Hi guys, sorry for the delay in the update in probability. I'm still coughing in a little bit, but we're going to try to get through a little bit of the probability notes so that hopefully you can master Chapter 7. Looking at the next area of probability, let's talk a little bit about the lottery. And the lottery is this idea that you go and you buy a ticket and you are allowed to choose 6 numbers. And if your 6 numbers match the 6 numbers chosen, then you win. And we start to think about, wow, how many different ways is there to pick 6 different numbers? Typically in the lotto, you can pick 1 through 50. And so you may pick a 2 and a 4, a 14, 44, 36, and 27 as your numbers. And it does not matter what order you get those numbers in, as long as they match those the state or whichever agency is doing that gets it. So we start thinking about, wow, how many different sets of 6 numbers would there be in 50? And what we realize is soon that that's just a little bit overwhelming. So let's take a look at a smaller example. And if we look at a smaller example, let's start with a sample set of 1, 2, 3, 4, and 5. And this is called a sample. That is, it's the items that we can choose from for the probability. First, let's choose ordered pairs. And if you recall about ordered pairs, order matters. X is different than Y. And so we'll begin listing them. We would have 1, 2, 1, 3, 1, 4, 1, 5. Those would be all the options with 1 being the first number. Then we can go over here and go 2, 1, 2, 3, 2, 4, and 2, 5. And those would be all the different numbers, ordered pairs that we could do for the number 2. And then we could start with 3, 1, 3, 2, 3, 4, 3, 5. Continuing on, we will go 4, 1, 4, 2, 4, 3, and 4, 5. And last, we would have 5, 1, 5, 2, 5, 3, and 5, 4. So in this case, what we realize is for each number there were 4 choices, and there were 5 different numbers. So we have 20 ways when order matters. That is, 1, 2 is different than 2, 1. But as I mentioned in the lottery, order doesn't matter. And when order doesn't matter, we need to get rid of the duplicates. So 1, 2, if order didn't matter, would be the same as 2, 1. 1, 3 would be the same as 3, 1. 1, 4 would be the same as 4, 1. And 1, 5 would be the same as 5, 1. 2, 3 would be the same as 3, 2. 2, 4 would be the same as 4, 2. And 2, 5 would be the same as 5, 2. 3, 4 would be the same as 4, 3. And 3, 5 the same as 5, 3. And then 4, 5 would be the same as 5, 4. So what you can see it did is it literally cut our choices in half, making, if order matters, there are only 10 different possibilities. This is an important way for us to think about the lottery ticket and how we have to change our thinking if we want to make sure we don't list all of the duplicates. So let's take a look at now what would happen of 5 numbers, but you had to order them with 3 different numbers. So instead of having pairs, we're going to have triples. So how many different triples could you, in fact, come up with? So pause the video here and try to make an organized list of all the different triples that you could make. Assuming now that you've pressed play again, let's take a peek. Well, we could have 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5, 1, 4, 5. So we know now that we would have 1, 2, 3, 4, 5, 6 different options using 1 as the first number. Then we could use 2, and with 2 we would have 2, 3, 4, 2, 3, 5, and 2, 4, 5, or 3 options. And last, we would have 3, 4, 5 for the last option, meaning that there would be 10 different ways to have 3 digits where order did not matter. If you could order those and it would be different, you would have 5 choices for your first number, meaning you could have picked 1 through 5. Now that you've picked one of those numbers, for the second digit, you only have 4 to choose from. And then you only have 3 numbers to choose from for the last digit. And we multiply these options together, and it's 20 times 3, or 60 different ways if order matters. That is, if 1, 2, 3 was different than 1, 3, 2, and it was different than 2, 1, 3, and that was different than 2, 3, 1, and 3, 1, 2 was different than 3, 2, 1. If all of those were different, then we were thinking about order mattering. We would have 60 different ways to choose 5 digits from 3 digits from a total of 5 possibilities. So what we know is for each time we have a set of 3, it's going to be listed 6 different times. Each time we have a set of 3 numbers. So 1, 2, 3 is going to be listed 6 different ways in this 60. So if we were to divide 60 by those 6 extra ways, we get the 10 that we saw on the previous. We get the 10 that we saw on the previous slide. So this is interesting to us to make sure that we understand when we want to find the number of possibilities in a situation where order doesn't matter, we have to divide off these duplicates so that we make sure that we are using only the possibilities that are unique. So with this idea, let's go back to our lottery. In our lottery problem, we were going to get to choose 6 different numbers, 1 through 50. So for this first number, we have 50 choices, 1, 2, 3, 4, 5, all the way up to 50. Whichever number we choose, we cannot choose another number, or that number again, because there are no repeats in the lottery. We need 6 distinct different numbers. So whatever number we pick, that one's no longer in the option the next time. So now, for the second number, we have 49 to choose from. And we keep that one out of the mix, and now we have 48 to choose from. And the pattern continues. Then we have 47 to choose from. We have 46 to choose from, and now we have 45 to choose from. And if you were to take a look and actually do that multiplication, 50 times 49 times 48 times 47 times 46 times 45, you would find that it is a very large number as it relates to possibilities. I made a mistake here, so I just need to erase that 4. And it is a 1, 3, 0, 4, 0, 0, 0. So 11,441,304,000 different lottery possibilities. Now you might be asking yourself, well, if they were only $1 a piece and I were a millionaire, why wouldn't I just go out and buy all 11,441,304,000 tickets, and then I'm guaranteed to win? As long as the jackpot was larger than 11 billion, I'm making money. First of all, I don't know how you would ever come up with all those possibilities in an organized way. Fill in all the dots at local 7-Eleven. But the thing that it didn't tell you is that most lotteries, somebody else, some lucky dog could come up with $1, buy a ticket at random, and split the pot with you. Now you're out half the money. So millionaires don't bother with this because there's no guarantee that they would get the whole amount of money, and that's a laborious process to go ahead and pick those. Now the problem we have with this number is this number, 11 billion plus, is assuming that if I would have chosen 1, 2, 3, 4, 5, and 6 as my numbers for the lottery, that 1, 3, 4, 2, 6, 5 is a different lottery ticket, and that is not the case. So it is important for us now to remember that in lottery, we have to take into account that those would be all considered duplicates. So in this 11 billion, we have counted too many possibilities. So we now need to figure out and divide away the extras. We need to do division. If we have 6 different numbers to choose from, that would mean that we have 6 extra numbers. We've listed it 6 extra times for the first number, 5 extra times for the second number, 4 extra times for the fourth number, 3 extra times for the third number, and 2 and 1. So whenever we have the total of 6 possible numbers that we're working with, we want to divide by 6 times 5 times 4 times 3 times 1. That is the same as dividing by 720. Now we realize that, this is a much better probability of winning the lotto, because now we are down to 15,890,700 tickets possible. So if you want to be the winning ticket and spend $1, you have 1 in 15,890,700 chances in winning. So it's very common to use lotto programs where they might say you can now only pick from 1 to 36, or you only get to pick 5 numbers. It's a common math problem going forward. The other thing that's really unique to probability is the idea of poker or card games. Card games will require you to understand the standard deck of cards. And the standard deck of cards, if you are just not familiar with, you don't use cards a lot, then go ahead and get a real deck of cards out and, make sure you have those. But let's just do a real quick summary in case those of you who don't know. So the standard deck of cards has 52 cards. And in those 52 cards, there are 4 suits. And in those suits, there are hearts, diamonds, spades, and clubs. Sorry, very poor club. These 2 are red. Hearts and diamonds are always red. Spades and clubs are always black. So if there are 4 suits and 52 cards, we know that each one, there are 13 hearts, 13 diamonds, 13 spades, and 13 clubs. That means there are 13 plus 13 are 26 red cards and 26 black cards. Aces can be considered 1 or greater than a king. So we have, it can be what we call low or high. Now, face cards are the cards that on a standard deck of cards, when you physically look at the card, you realize that it has a face of a character on those. Face cards are Jack, Queen, and Kings. Aces do not have faces on them, so Jack, Queen, King are considered face cards. So that gives you a little update just on the deck of cards. Now let's take a look at what it might look like to figure out the probability of a few poker hands. Poker, we are just going to assume that you are trying to draw from a standard deck of cards to see what kind of poker hand you could get. And what I'm wondering is, first of all, how many different five-card hands can you come up with? How many different ones? Now remember, think back when you're playing cards. If somebody deals you cards, you pick them up and reorder them in your hand all the time. So the order does not matter. The order in which you're dealt these cards does not matter. By the way, that were the dogs, so bear with it. The order doesn't matter, so what we know is for the first card, we would have 52 choices. For the second card, we have 51, 50, 49, and 48. And of those cards, that would leave us with this many choices. 311,875,200 different five-card hands if order mattered. But since we just said order doesn't matter, then we know we have to divide off the duplicates. If we divide off the duplicates, we know that we need to divide by 5 times 4 times 3 times 2 times 1, or simply divide by 120. So the total number of five-card hands turns out to be 2,598,960. So that is always our denominator in probability because that's the total number of five-card hands we can come up with. Five-card hands. So now, if we were interested in something specific like how many four-of-a-kind hands could we have? That is ace, 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 or you could have jack, 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 king, 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 something like that. We have 4 in a row plus another card. How many different hands do you think you could have for that? Go ahead and try that. Go ahead and pause the video and give that a try. Now that you've thought about it, let's just take the scenario for ace. This would be the best hand you could come up with. You would be excited to get dealt this and then 4 aces and then any other card. So you would have the 4 aces means that there are 48 cards left here, which is 52 cards total, minus your 4 of a kind, means that you have 48 left. So this could be a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, a jack, a king, and a queen of hearts, and then diamonds, then spades, then clubs. So 48 different cards with 4 aces, and then substituting in right here all those different possibilities I just listed. So we can imagine that there would be 48 different ones for the kings when you have 4 kings, and 48 different hands for 4 jacks, and 48 different hands for 4 fives, and so on. So what we know is that we must have the idea that there are 13 different ways to have 4 of a kind. You could have 4 aces, 4 kings, 4 queens, 4 jacks, for tens, whatever, you would have 13 different four of a kinds. And you would have for each one of those, you would have 48 different ways to make a 5-card hand by adding in the 48th card. 13 times 48 equals 624. So the probability of getting a 4 cards alike in a 5-card hand is equal to 624 out of those total possible 5-card hands, which works out to be very much a small probability that that would happen. So almost unlikely. So you're very excited when you get a 4 of a kind hand. Now, if you think about what it would be like to get a straight flush, and I'll explain what a straight flush is. A straight flush is getting 5 cards, sequence, same suit. Is called a straight flush. That is the idea that you would get an ace of hearts, a 2 of hearts, a 3 of hearts, a 4 of hearts, and a 5 of hearts. So they're all in a row. The other possibilities that you could come up with would be you could then get a 2, a 3, a 4, a 5, and a 6, or a 3, a 4, a 5, a 6, and a 7, or a 4, a 5, a 6, a 7, and an 8, 5, 6, 7, 8, or 9, 6, 7, 8, 9, or 10, 7, 8, 9, 10, or Jack, 8, 9, 10, Jack, Queen, 9, 10, Jack, Queen, King, and we cannot forget that we could also have a 10, Jack, Queen, King, Ace. And those would be all the different 5-card sequences we could get in hearts. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different ways that we can get a 5-card sequence in hearts. So we must have a 10 different ways in diamonds. Oops, sorry, bad diamond. We must have 10 different ways in clubs. And we must have 10 different ways in spades. So we must have 40 different ways that we could get a 5-card sequence. So the probability of getting that is now 40 over the 2,598,960. So, again, now we are talking about 000014. Extremely unlikely to get a straight flush. Well, I hope this short lesson on probability helps you understand a little bit about what might happen in a card scenario, a lottery scenario, and why we have to make sure we consider duplicates. I have one more short segment that I'll be providing you on the words and or in probability. Then we'll be also moving on into Chapter 8, which is statistics. So just real briefly, I'll go to one more slide. In probability, if you see the word or have to say to yourself and, it means multiplication. That is, what is the probability of getting a 6 on a die and tails on a coin? The probability of getting a 6 on a die is 1 out of 6. And the probability of getting a tails and a coin is 1 out of 2. So 1/6 times 1/2 is equal to 1/12. And that is a probability of getting both a 6 and a dime. And if we were to draw a table and list all of the different possibilities for a die, and then list all the possibilities for a coin that you could have gotten with each. What you soon realize is there's only one time that you would have gotten a 6 and a tails, and only one time you got 6 and a heads, and only one time you got 5 and a heads and 5 and a tails. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different possibilities, and only one of those right here is a 6 and a tails, making it 1 out of 12. So and always means multiplication. The word or is more about addition and subtracting off duplicates. More or means to use addition and subtract off duplicates. For example, if I were to ask you the probability of getting a 9 or a heart in a standard deck of cards, first of all, we know the denominator is 52 because there are 52 cards. There are 4 9s in the deck. There are 13 hearts in the deck. And that tells me that if I were to add those, it's 17 out of 52% chance of getting a 9 or a hearts. However, if I asked you to take a standard deck of cards and pull those all out, you would have had an ace, a 2, a 3, a 4, a 5 of hearts, a 6 of hearts, a 7 of hearts, an 8 of hearts, a 9, a 10, a jack, a queen, a king, and then you would have had the 9 of diamonds, you would have had the 9 of clubs, and you would have had the 9 of spades. That does not equal 17 because it's important to know that you already counted the 9 of hearts when you counted the hearts. So now we have to subtract off one duplicate because the 9 of hearts is both, and we get 16 out of 52, which is the correct answer.